In this section, we'll look further at energy transfers in circuits, mains electricity and electric charge. First, energy transfers in circuits. In the Foundation Physics programme, we looked at the symbols for the basic components of circuit diagrams. For the higher tier, you need to know a few more. A diode, a light-emitting diode, a light-dependent resistor, a fuse, a thermistor, and an earth connection. In the Foundation Physics programme, we saw that there's a special relationship between voltage, current and resistance in a circuit, called Ohm's law. Ohm's law says that anywhere in a circuit, V equals I times R, where V is the voltage across a component in volts, I is the current going through the component in amps, and R is the resistance of the component in ohms. If you know any two of these values, you can work out the other one. Here's a sample question that uses Ohm's law. A bicycle has different sized bulbs for the front and rear lights, using the same battery. If the filament in the front lamp has a resistance of 3.4 ohms and it takes a current of 0.7 amps, what voltage does it work at? The rear lamp works at 0.5 amps. What is its resistance? Now, we're told that the current through the front bulb is 0.7 amps and that the resistance is 3.4 ohms. From Ohm's law, we know that the voltage V equals I times R, the current times the resistance. So V equals 0.7 amps times 3.4 ohms. That's 2.38 volts. So the battery is supplying 2.38 volts to the front bulb. Now for the second part of the question. We're told that the current through the rear bulb is 0.5 amps, and we've just worked out that the voltage both lamps are using is 2.38 volts. We can work out the resistance using Ohm's law again. We know that the resistance R equals the voltage V divided by the current I. That's 2.38 divided by 0.5 equals 4.76 ohms. Some components do not obey Ohm's law. They're called non-ohmic conductors. A bulb filament is a non-ohmic conductor. As the voltage across a bulb filament increases, it gets hotter and its resistance increases. A current voltage graph for a bulb filament curves downwards as the voltage increases. That's because the resistance is increasing and reducing the rate of increase of the current. A thermistor is another non-ohmic conductor. Thermistors are made of ceramic semiconductor material, not metal. Unlike a normal resistor, the resistance of a thermistor is lower at higher temperatures. Thermistors are used to measure and control temperature, for example in a thermostat. A light-dependent resistor, or LDR, behaves in a similar way. If the intensity of light shining on an LDR increases, the resistance falls, and if the intensity decreases, the resistance increases. LDRs are used to switch circuits on and off automatically as the ambient light level changes, like in streetlights. A diode is made from semiconducting material that allows current to flow through it in one direction only. Its resistance in one direction is very low, and in the other direction it's very high. Diodes are used in many electronic circuits. The current voltage graph for a diode shows that current flows for positive voltages, but no current flows for negative voltages. That's the end of this higher tier section on energy transfer in circuits. Next, more about mains electricity. Generators and batteries are sources of energy, and the electrical current transfers that energy from the source to the components in a circuit. The rate at which the energy is transferred to a circuit is called electrical power. Power is measured in watts, or kilowatts. That's 1,000 watts. We use the same expression about electrical appliances. A 3 kilowatt electric fire consumes 3,000 watts of electrical power. Power in watts equals voltage in volts times current in amps, or P equals V times I. Just like Ohm's law, if you know any two of these, you can work out the third. What is the most power a fused 13 amp plug can carry safely? We know that power equals voltage times current. In this case, mains voltage is 240 volts, times the 13 amp limit of the plug. That's 240 times 13 equals 3,120 watts. So the safe limit of a 13 amp plug is just over 3 kilowatts, enough for an electric fire. Here's another useful formula. We said that power is the rate at which the electrical energy is transferred to a circuit. That means power equals energy divided by time. Put another way, energy equals power multiplied by the time in seconds. That's E equals P times T. The unit of energy is joules. Here's a question about electrical energy. A kettle has a power rating of 2.4 kilowatts. It takes 5 minutes to boil. How much energy is used? The question is asking how much energy the kettle uses. Now we know that energy in joules equals power in watts times time in seconds. We know that the power consumption of the kettle is 2.4 kilowatts and it's on for 5 minutes. If we put them in our formula, then energy E equals 2,400 watts times 5 minutes times 60 to give the time in seconds. That's 720,000 joules, or 720 kilojoules. Your home electricity meter measures the amount of electrical energy used, so they can work out your electricity bill. Because joules are so small, a more practical measure of electrical energy is kilowatt hours. That's the energy used by a 1 kilowatt appliance for 1 hour. So the energy formula becomes energy in kilowatt hours equals power in kilowatts times the time in hours. 1 kilowatt hour is the same as 1 unit of electricity we pay for. So here's another question about our kettle. If the 2.4 kilowatt kettle is used 6 times a day for 5 minutes each time, how many units of electricity does it use in 1 week? The question asks how many units of electricity the kettle uses, but we know that units of electricity are the same as kilowatt hours, which is a measure of electrical energy. That means we can use our energy formula. Energy in kilowatt hours equals power in kilowatts times the time in hours. So E equals 2.4 kilowatts times 6 times a day times 5 minutes divided by 60 to give the time in hours times 7 days in a week. That simplifies to 2.4 times 1/2 times 7. That's 1.2 times 7 equals 8.4 kilowatt hours, or 8.4 units of electricity. That's the end of this higher tier section on mains electricity. Now some more about electric charge. In the Foundation Physics programme, we saw that an electric current is the movement of negative charge. For the higher tier paper, you need to know a bit more about the relationship between electric current and the flow of electric charge. The symbol for electric charge is Q. Charge is measured in coulombs. The symbol for electric current is I. Current is measured in amps. A current of 1 amp is the flow of 1 coulomb of electric charge per second. That's amps equals coulombs divided by seconds. Another way of saying that is that charge equals current times time. So 4 amps of current flowing for 30 seconds is moving 4 times 30. That's 120 coulombs of charge. Another formula to make a note of is that the voltage of a battery is the amount of energy in joules that the charge is carrying around the circuit. So 1 volt equals 1 joule per coulomb. That's the end of this higher tier section on electric charge.